Section 27.5, diffraction. Diffraction is something that's similar to interference, but it's actually a little bit different. So interference, we have at least two sources of light or of some sort of wave that are interacting with each other. Diffraction is just one source, and it's focused on how that source can bend around obstacles or the edges of an opening, and that source can effectively interfere with itself, which is strange. How is that? Well, it comes in part from Huygens' principle that every point on a wavefront acts as a source of tiny wavelets that move forward with the same speed as the wave. The wavefront at a later instant is the surface that's tangent to these wavelets. So if we imagine that there's a plane wave front of, say, sound, we could look at sound here, and as it passes through an opening like a doorway, we could look at 5 points within that sound wave passing through the opening, and each of these produces its own wave going in all directions. So we would do a uniform circular shape around that, or semi-circle around that, since it's going forward. And because of that, when you sum them up to produce the overall wave at a later instant, it's no longer traveling in a straight line. The sound wave has now bent around the opening. And that means the listener who's around the corner, who's not right outside the door, can still hear the sound. This is something you've observed if you're, say, walking up to a corner and you hear someone else from the other side, like around the corner from you. It could be a reflection that the sound is bouncing off, but in many cases, it's just an instance that the sound is able to diffract or bend outward around the opening. And this bending of sound can occur with light as well. So without diffraction, if you shine a light on a narrow opening, you just get a narrow opening on the end. It illuminates whatever the pattern is that's here. But in the conditions of diffraction, which usually mean matching the wavelength and the width of this slit opening to be just right, you get this very different effect. You get a much brighter and wider spot in the middle that's wider than the opening. And then you get these key dark fringes here with light that's extending. It's bending around the corner to be much wider than just the opening itself. So what's going on here? Well, once again, the incident plane wave can be considered to have 5 different sources, right? And at the very middle, we could consider, hey, all of these are going to meet in the middle there, and that's going to produce a bright spot because of the symmetry of it. Now, if you shift off of that central bright fringe, then there's going to be some destructive interference. And there can be a point where, say, with 1 and 3, 3 is half of a wavelength longer, and 5 is a full wavelength longer, and that produces a dark fringe that's offset from the central bright fringe. So this is interesting. This is a little bit different than our double slit experiment with interference. As a result, our pattern looks something like this, where there's a very bright central fringe that has some midpoint, and then there are these dark fringes, and the dark fringes are actually more distinctive and easier to measure than the bright fringes, which are somewhere, midpoints of them somewhere in there, right? They kind of get smeared out after that first one. So what we actually have with diffraction, with a single slit, with a one opening, is we have a condition to find the dark fringes for this. That sine of theta now, instead of giving the bright fringes, only gives us the dark fringes. It's equal to m times lambda, the wavelength of the light, divided by w, which is the width of the slit, how big that is. And m here, notice, is 1, 2, or 3. It can't be 0, because 0 is not a dark fringe. That would be right in the middle, where it is definitely bright, very bright there. So I would make sure when you put this on your crib sheet to include the words here that this is dark fringes for single slit diffraction, because it's one of the main challenges with chapter 27 is figuring out which equations apply to which scenarios. And one more note, I mentioned something about the conditions for diffraction. The key here is going to be this ratio of wavelength to width of opening, right? So here they show the width of the opening. This is really cool to actually get a visual of this. And the wavelength is shown between the crests here, right? The ridges, that would be a wavelength between crests. And so there's some slight diffraction when it's pretty wide relative to the wavelength, when it's a pretty small lambda over W ratio. But if we increase lambda over W, the bending or the diffraction gets bigger. So notice the slit width is a lot smaller here, wavelength's even bigger, and the diffraction is much bigger. So the angle equation to get to that first minimum, that angle becomes larger. And so you start seeing the effect of more diffraction. A cool thing with diffraction is it doesn't have to just be a vertical slit. You could also do this with a circular opening or even an opaque disc. And I would expect if you shine light at an opaque disc, you get a shadow of that disc. And you do get a shadow, but within that shadow, there's regions of constructive interference, right? There's a bright ring in the middle and then some other rings around it. So the key here is we'll be able to measure the distance to those dark rings because those will be the first dark fringes, but they're now circular instead of vertical. Now this has some important implications for something known as resolving power, which is section 27.6. And to think about resolving power, I want you to think about a car approaching from far off, right? When it's super far away, you can just barely see the headlights, and they look like one headlight. As it gets closer, you can start to see resolve that there are two separate headlights, right? Especially if it gets really close. It's like, okay, there are definitely two headlights here. But when it's far off, it's pretty hard to tell if it's a motorcycle or if it's just a car that's really far away. And so resolving power says, how close or how much do you need to be able to see in order to be able to tell if there are actually two headlights or if it is just one and that's all there is. And so we're going to use diffraction pattern with a circular diffraction. Here they show it with a circular opening, a hole. It's the same thing as if there's just a circle there blocking the light. And what we have is there's a very bright central maxima, but then we have a condition to the first minimum, to the first dark fringe. And that condition can be given by sine of theta, where theta is the angle from the midpoint out to that dark fringe, is equal to 1.22 times lambda divided by d, where d is the diameter of this hole. So it's yet another equation, but this tells us about a circular diffraction pattern, and it only gives us the first minimum. We won't worry about any higher minimums, just this first one. And why this matters is we could imagine having two objects coming through a camera aperture, and they then pass to the image sensor, and our camera will be able to resolve them as long as they are separate enough, as long as they aren't on top of each other. So that will be something to keep in mind with resolving these. And so this brings us to something known as Rayleighs criterion, that 2 point objects are just resolved when the first dark fringe in the diffraction pattern of one falls directly on the central bright fringe in the diffraction pattern of the other. So notice these two are still very resolvable. You can tell there are 2 peaks here. And they'd go even a little further if it was the peak and the dark fringe was actually overlapped with the bright fringe of the other. And so the key here is that the minimum angle to resolve objects is going to be our condition for that first dark fringe. that's going to be 1.22 times lambda, the wavelength, divided by d, the diameter of that opening of the aperture. And here we've gotten rid of the sign. It's a slight approximation to just call it the angle theta, but it's a reasonable one. So we can just say that angle is given by this condition, where it's a larger angle if you have a larger wavelength. So you need a larger angle to resolve it, or you would need a larger angle to resolve it if you have a smaller opening. You won't be able to resolve things quite as well. So looking at an example of this, first an introduction. French post-impressionist artist Georges Seurat developed a technique of painting in which dots of color are placed close together on the canvas. From sufficiently far away, the individual dots are not distinguishable, and the images in the picture take on a more normal appearance. So this is really cool, right? The picture looks pretty normal from our view, but if you look close up, they're just little dots of paint. Suppose a person stands close to the painting and then backs up until the dots just become indistinguishable to his eyes and takes a picture from this position. The light enters his eyes through pupils that have diameters of 2.5 millimeters and enters the digital camera through an aperture or opening with a diameter of 25 millimeters. He goes home and prints an enlarged version of the painting. Can he see the individual dots in the photograph? One option, no. If his eyes can't see the dots at the museum, the camera is unable to record the individual dots. B, yes, the camera gathers light through a much larger aperture than the eye. Or C, yes, unlike the eye, a photograph taken by a camera is not limited by diffraction. So I'd like you to think about this. Go ahead and hit pause so you have a moment to do that. All right, let's take a look. So it is B. The camera and your eye are very different in how they take things in, so they can see different things. So that's why it's not A. The camera, though, is still limited by diffraction, so it's not C either. And the key is that the camera, though it's limited by diffraction, has a much larger opening. Since the angle is inversely proportional to the opening, if you have a larger opening, you don't need as large of an angle to be able to resolve the differences. And so the camera, if the person can just barely not resolve it and the camera has a diameter that's 10 times bigger, the camera definitely will be able to resolve those dots, which is pretty nifty. So there we have it. That introduces diffraction and resolving power.